Welcome to Chemical Kinetics, and in this topic we're simply going to be discussing the speed of chemical reactions. So chemical kinetics simply discusses how fast or how slow a chemical reaction is taking place, and this can be considered with regards to how fast the reactants are being used up or to how fast the products are being formed. So whenever you have a chemical reaction, let's have a chemical reaction that is balanced in this manner. So the small letters are representing the integers that are balancing the capital letters. So the capital letters should be taken as if they are compounds. Then we have the small letters representing the integers balancing them. So if this is what you are having, these are the reactants and these are the products this side. So we know the whole essence of chemistry is that we take certain reactants to get desired products. That's what we just want in chemistry. That's the whole idea of having chemical reactions. Now, under chemical kinetics, we're interested in knowing how fast this process is going to happen or how slow it's going to happen. So whenever any reaction is happening, and we want to measure the speed of the chemical reaction, we can either measure how fast the reactants are being used up. So that's what we call the rate of disappearance. So the rate of disappearance, because they're disappearing, then someone else can just sit and wait to see how much is obtained. This is the rate of appearance. So we can just measure how much is being produced. Yeah, so take for example, someone is baking, right? Then you want to find out the speed of the whole process. You can be checking how fast they're using the ingredients, the baking powder, the yeast, everything that they're using. Or you can just sit back and relax, be counting the scones or whatsoever that they're baking. Then you know in an hour they're producing how many scones, right? That's basically what you can simply do. So the speed, or rather the rate of a chemical reaction, whether slow or fast, can either be measured in any direction. And when it comes to reactants, since it's the rate of disappearance, we're just going to say the rate of a reaction is just going to be equal to negative the changes in the concentration of the first thing, which is A, over the changes in time. But then A had a coefficient which was small letter a in front. So when we are considering the rate of the reaction, we want it to be per molecule, despite the number of molecules that are present. So if there are 2 molecules of A, we want to find out at what rate is 1 molecule of A being used up. So now that we are dividing with the coefficient, which is in the balanced equation, now that we are dividing with it. And the speed of the chemical reaction can be studied with respect to any of the species in the chemical reaction. So someone who observes the rate at which A is disappearing will get the same answer as someone who is observing the rate at which B is disappearing, or someone who is observing the rate at which C is being formed or appearing. So when it comes to reactants, because they are disappearing, they are reducing, we put a negative in front of the changes in the concentration. So someone who uses A and someone who uses the changes in the concentration of B, then divided by the change in time with small letter b, or someone who observes the changes in the concentration of C divided by time divided by C, or someone who observes the changes in the concentration of species D with respect to time, then divided by the small letter d, which is balancing it on the chemical reaction. They will all obtain the same answer. That's basically what we are saying. The reason why we are putting a negative on reactants is because they are disappearing, they are finishing. The only way these two can be similar, I mean these comparisons can be all equal, is by negating the changes in the concentration of the reactants. So what I mean is this, guys. Let's say you have 0.5, right, molarity of A. So ingosila, this guy is being used up, meaning after a certain period of time, this is when the time is 0 degrees, 0 seconds, right? Then after a certain period of time, let's call it T2, after 2 seconds, the concentration of A reduces to, let's say, 0.3 molarity. That's UA, right? So we're going to say, what is the changes in the concentration of air. What is the difference between the final that we are having? The changes in the concentration of air will be 0.3 molarity minus 0.5 molarity. You notice that the answer is going to be negative, right? Because it is reducing. So to counter that negative answer we're going to get, no wonder we are putting a negative on the rate of the reaction with respect to a reactant. So this is what we are having. These are just the rate of the reaction, the format that we use to explain the whole idea of the rate of disappearance to be equal to the rate of the appearance. So before we even dive into this, please don't be confused. We're just saying in chemical kinetics, we want to study the speed of the reaction. And there are certain factors that we need to talk about that influence the rate at which a reaction is happening. So the following are a need to know basis. These are factors that will either speed up the reaction or slow it down. So first and foremost, we'll talk about temperature. Now we have to be very careful here when we're discussing temperature. So in high school, you used to say increase in temperature will speed up the chemical reaction, right? Because you expect, for example, if you're trying to dissolve sugar. So if you use hot water, sugar will dissolve at a fast rate. If you use cold water, it will take time, right? So here we're going to specify the changes in temperature. Are we increasing the temperature or decreasing the temperature? But then we have to consider whether the reaction we're dealing with is what? Endothermic or exothermic. So if the chemical reaction is endothermic and you increase the temperature, it simply means you speed up the chemical reaction. It will become what? It will become faster. That's basically what we are saying. But if you reduce the temperature, it becomes what? Slower. So if you increase the temperature, it becomes faster. If you reduce the temperature, it becomes slower. If it's an endothermic reaction, meaning it needs heat, right? Then if it is an exothermic reaction and you're increasing the temperature, it becomes slower because the reaction is trying to get rid of heat and you're adding heat, so you're slowing it down. So that's simply a reduction in terms of how fast the reaction is going to take place. The rate is going to be slow. But if it's an exothermic reaction and you are going to decrease the temperature, the reaction becomes what? Faster. It already doesn't want heat. It's trying to get rid of heat. Then again, you're decreasing the temperature, meaning you're supporting it to lose heat. So meaning the reaction will become what? Faster. So the next time they ask you to say, what happens to a chemical reaction when you change temperature? You have to ask the question to say, is the enthalpy or is the energy of that reaction positive or negative? So how do you know it's endothermic? The enthalpy of the reaction, which is the heat of the reaction, is going to be positive. That's how you know to say this reaction is endothermic. If the value of the energy of that reaction is negative, just know it's what? Exothermic. That's how you can tell. So this is one of the factors that can affect the rate of a reaction. The second one, we have the size of particles. So this is still the same thing you used to discuss in high school. The smaller the particles, the faster the chemical reaction, because it's easy to deal with them, right? It's easy to react with them. Yeah, so this is still the same explanation you had in high school. Then C, the existence of a catalyst or the usage of a catalyst. So if you use a catalyst, the reaction speeds up. For example, washing. You can wash with water, but you cannot remove stains, right? You use soap. Soap contains some synthesized enzymes which will react as catalyst. So they will speed up the process and then washing will be easy. So this is a typical domestic application of how a reaction can be speed up. Yeah, so the existence of a what? A catalyst. Then apart from this, if it's in a gaseous phase, we're going to have the influence of pressure. So if it's in a gaseous state, meaning it's in a homogeneous, everything on the reactant side and on the product side is in a gaseous state. That's what we call a homogeneous reaction. Homogeneous reaction just means it's one state of matter throughout. Could be liquid, could be aqueous, could be solid, could be gases. So if it's in gases, meaning changes in the pressure will affect the chemical reaction, because there's this under gases you learn to say pressure times volume is equal to the number of moles. Then you have what? You have RT, right? So pressure is the same as, we divide by V here, V. So this is number of moles over volume. That's the same as concentration times the universal gas constant and temperature. So increase in pressure will speed up the chemical reaction because it will entail that there's going to be an increase in the concentration. Yeah, so this goes hand in hand with concentration. Whenever you increase the concentration, meaning you are speeding up the chemical reaction, you are supporting it. Yeah, so these are some of the factors. There's also something you used to talk about in high school. You were talking about what? The surface area, right? The larger the surface area, the more faster the chemical reaction. And also the changes in your volume. Yeah, we'll discuss about it later on, but then we can just put it out here. We'll talk about it mostly when we discuss chemical equilibrium, but also the changes in volume. So you have to be careful here. When you increase the volume, you slower the reaction down, because increase in volume means decrease in the concentration. When you increase the concentration, the reaction becomes faster, right? When you decrease the concentration, the reaction becomes slower. So whenever you increase the concentration, the reaction becomes slower because concentration and volume are inversely related to each other. Remember, concentration is equal to number of moles over what? Volume. So meaning concentration is inversely proportional to volume. Increase in the volume will entail that there's a decrease in what? In concentration. So meaning you're slowing down the chemical reaction. So these are some of the factors that you have to have, that you need to put on your fingertips, the ones that you need to very much know and be able to explain. So this is what you need to know. Then aside from this, there's a part which you need to know, what we call molecularity. So molecularity is simply you telling us the number of reactants that are responsible, that are present in a particular chemical reaction. So if there's only one particular reactant in a chemical reaction that is responsible for the production of our products, it's called a unimolecular reaction. Yeah, so the molecularity will just be unimolecular. This is the molecularity. That's a name that we give to that particular chemical reaction. Then if you have two, they could be the same thing or they could be totally different. For example, A plus B. Either we're just saying if these are responsible, if they are countable as 2. So this is the same as 2A, right? And then they are both responsible for the production of for the existence of the products. We call that type of a reaction to be a bimolecular reaction. So RxN will represent reaction. This is reaction. Then if there are 3 things, they could be the same things, or they could be totally different, or 2 things can be the same, one could be different, or they could be totally different. All of them are different. We really don't mind, as long as they are all responsible for the products formed. This is called a thermolecular reaction. This is what we have. Now, remember we said we're interested in getting the rate or knowing the speed of the chemical reaction. So we have to know the reactant which is responsible for the products to be easily formed. So in short, we're just saying, unlike having the freedom of choosing between what you had, so there's what we call here, there's what we call rate law. There's this guy here. So from what we had previously, I gave us an expression that looks like this. We said everyone is at liberty to choose what they want to study to tell us the rate of the reaction. But then they came up with an understanding to say, instead of leaving people to choose what they want to use, why not have something standard that everyone is going to be following? So now they came up with the idea of the rate law to say the rate law is simply, rate law is simply equal to the rate constant. There's what we call a rate constant, multiplying the concentrations of the reactants alone. So here you can put any number that you want. We call this, I'll just put an N there, and then we can have what? The reactants, then you can put your M there. So if there are 5 or 3 reactants, you put all of them, then there should be letters on top of them. So the K is what we call the rate constant. It's the constant which connects the rate of the reaction and the concentrations of the reactants. And then this here, when I say something like this, this means the concentration of A. That's what it means. When I say this, it means the concentration of B. That's what you have. And the N and the M, so N is called, this is going to be called the order of A, and then small letter m here, the power of B is going to be called the order of B. And when we sum them up, when you add small letter n and small letter m, when you add the n and m, they will give you the overall order of the chemical reaction. Overall order of the chemical reaction. So we have a general thing. We're saying let everyone be using what? Reactants to study or to find out the rate of a chemical reaction. And what we mean by the order of the reaction is simply the number of times that the reactant given is going to affect the rate of the reaction. So the rate is here. We're just saying if the N here is 2, meaning changes in the concentration of A will double the what? The rate of the reaction. And the N and M should never be gotten from the balanced equation. We don't get these numbers here to put as the powers there. No. These are always supposed to be calculated from experimental data that they'll be giving you. So questions that have to do with the rate of flow will always be coming with a table. They'll always be giving you a table, and in the table you only have, or you will only be seeing reactants given in terms of the concentrations, and then they'll tell you the rate at each particular experiment that was run. Okay, so let me just take this back again. We are saying everyone is at liberty to choose what to study, right? So if someone is baking, let's take someone is making fritters. We can just look, someone can focus on the what? On the baking powder and find out how much it's being used in what? In an hour or in 30 minutes or something. Someone can focus on the what? The cooking oil, or how much the electric units, the ZESCO units are being used up. Then we'll know how much or how fast the reaction is happening. Or someone else can just sit back and start counting the scones that are being produced or the fritters, whatsoever is being made. Now we're saying to avoid all that freedom, let's be having something uniform. Let us always be using what? Reactants all the time. So we are going to be only using reactants. And the relation between the reactants and the rate of the reaction is what we are calling to be the rate law. And on the rate law, there's always going to be a constant, a number connecting the rate of the reaction and the concentrations. Though the concentrations are going to be equated to the what? They're going to be equated to the powers that are called the orders. So there is a certain integer that A is affecting there is a number that A can be given that shows how much it's affecting what? It's affecting at the rate of the reaction. The same applies to B. So these are what we call orders, and they can never be negative or fractions. That's one thing you must know. So in case you get the order to be negative, just know you have done something wrong. And when you add the orders like this, when you add the N and the M, they will give you the overall order of the reaction. So we cannot say this is a 0 order, or this is a first order, or second order, third order reaction. So the order will tell us the impact of the changes that we'll make in the concentration on the rate of the reaction. So in case that is not making sense, I'm just saying questions that have to do with the rate law, they'll always be coming with a table. So this is a typical illustration that I've given you here. They are saying, given the data table below, find the rate law. So we need to get the rate law, order of each reactant, and overall order of the reaction. So you notice the reaction given here. This is in aqueous, by the way. This is in aqueous, this is in gas, this is in liquid. So this is what you are given. This is the reaction. And on the reaction, we try to notice that nitrogen, what? Nitrogen is balanced, is it? Nitrogen is balanced. We're seeing NN. Here is the N2. We are seeing that. We're seeing hydrogen is balanced. Oxygen is also balanced. So the reaction is what? Is balanced. And we are saying we only get the reactants. So to solve this type of a problem, we're always going to be getting the reactants only. So you focus on the reactants. You focus on this. Only on the reactants. Even if there are 3 of them, write them all down. So we'll say the rate is equal to, you put a K, then you put the first reactant, which is ammonia ion. You put this guy here. Put an N there, or any letter that you want. Then you come, you put your nitrogen dioxide ion here. Put any letter that you want. I'll use M. So some people can use P or Q. It's up to you. You can use any letter that you want. All we are saying is that you have to get the value of N and M using this experimental data that they will give you. So this is the first step. So step number 1, we are done. We have created the rate law expression. So this is the rate law expression. It's called an expression yet because we don't know what K is, we don't know what N is, we don't know what M is. That's what we have. And you'll be given trials or experiments. So they are saying, in the first experiment, when the concentration of ammonia ion was 0.1 and the concentration of nitrogen dioxide ion was 0.001 molarity, the rate was this. That's what they're telling us. Then when they keep the concentration of ammonia constant and they double the concentration of nitrogen dioxide, look at what happens to the rate. It also what doubles, right? Then when they double the concentration of the ammonia ion and leave this guy constant, look at what happens. This again, it doubles, right? That's what you're having. So we want to use this table to find out what N and M are. After we are done, we're going now to find what K is. So we find N and M first, then we'll get what? K. So there will always be a table whenever they need you to get the rate law. So please have that in mind. And the first thing that you do is to find 2 experiments where one concentration is kept constant and the other one is changing. So I'll choose experiment 1 and 2 because look at the concentration of ammonia ion. It's kept constant. It's 0.1 and here it's 0.1, right? When the concentration of nitrogen dioxide is changing, you are seeing that has changed, right? So I'll just do the replacement. So I've chosen experiment 1. I'll divide it by experiment 2. We always divide the experiments that you've chosen. You can either divide it the other way around. Even if you divide rate number 1 or experiment 1 by 2 or divide experiment 2 by 1, the answer is always going to be the same. So we're going to write the information on the first experiment, which is R1, this experiment here. So let me just say I'm dividing for the sake of clarity to avoid people getting confused. We're saying we are dividing experiment 1 by experiment 2. We start with the rate. We are following the expression. What is the rate of experiment 1? It's 1.37 times 10. So 1.35 times 10 to the power negative 7 is equal to, no need of showing units here. We don't have to show units here. You will only show units when you are calculating for the value of K. So the experiment 1, the rate is that. K we don't know. The concentration of ammonia we know it's 0.1, 0 molarity. We have an N there. The concentration of the nitrogen dioxide is 0.05. This is to the power N. Then we are dividing this whole thing by experiment number 2. The rate of experiment number 2 is 2.70 times 10 to the power negative 7. Then there's a K. There's 0.10 to the power N. And there's 0.01 to the power M. So just pause this and try to see what is happening here. We are taking all the information about experiment 1, following this expression here. This is what we are following. So in the rate, we put the rate. K, we leave it there because we don't know what K is. The concentration of ammonia, we're picking it there. This is what you're having. We picked this. The concentration of the nitrogen dioxide in experiment 1, we are picking this guy there. That's the first part on top. Then we do the same for the bottom, and we are dividing experiment 1 divided by experiment 2. So what led to our choice? We've said we choose 2 experiments all the time. You choose 2 experiments where one concentration is kept constant and one is changing. That's how you handle it if you have 2 reactants. We had ammonia ion and the nitrogen dioxide ion. So meaning we need to keep one constant and one should be changing. Why do we need that? Because we need this expression down here so that the part which is similar cancels out. The K's are going to cancel. This part which is the same, which was kept constant also cancels. We divide the rates this side. We have 1.35 divided by 2.7. So according to my calculations here on my calculator, I'm personally getting a 0.5. This is simply the same thing as 0.5. Then on the other side, the powers are the same. So 0.005 to the power m divided by 0.01 to the power m. If the powers are the same, it's the same as you just dividing 0.005 over 0.01. This everything to the power m. It's one and the same thing, right? Because the powers are the same. Then down here, remember we said we cannot have fractions or negatives, so we're going to write it in a fraction form. Then this side, we're saying 0.005 divided by 0.01. It's also giving me 1.5. This is raised to the power at m, right? Here, this is half as well, there's a 1. The bases are the same. This is half and this is half. Or if you don't want to see this, you can use the mathematics. For those that still remember their indices, this is the same as 2, like this. Then this is the same as 2 negative 1 is the same as 2 negative m. We just multiply negative 1 by m. So now the bases are the same. You can now equate the powers. Negative 1 is equal to negative m, meaning m is simply equal to what? 1. So you've gotten the value of m by using experiment 1 and 2. So we divided here. This is what we got. The bases are the same. So here we could have just gone direct and said 1 is equal to m. We would have gotten the same outcome because half and half, they're the same, right? The powers also will be or should be the same. So this is the first order that we are getting. So if we go back to our equation, the rate law, we're saying we know what m is. M is simply what? A 1. Once you know m, you put it back there. Now what is left is for us to know the value of n. Now the first time we didn't know either n or m, so no wonder we're saying we always choose 2 experiments. You would have chosen experiment 2 and 3 because this is constant and this is changing, right? That's what we said. Just choose 2 experiments where one concentration is constant and one is changing. Then divide them. That's the first thing that we did. Now that we know m, our choice is going to be influenced in such a way that we need to choose 2 experiments where the ammonia, which has the n that we don't know yet, is changing. Because we can't keep it constant. If we keep it constant, it will cancel like the same way that it cancelled here. So we have to choose 2 experiments where n is changing. So now we're simply going to choose experiment 2 and 3. So I'll choose this because you are seeing that it's changing. It becomes that, right? So we're going to go back to our rate law. This is the rate. The rate is equal to, we have K. This is NH4 plus, this is there's an N there. This is N2 negative. There is an M here, but we know what M is 1. So we're saying we're dividing experiment 2 divided by experiment 3. That's what we are doing. Why are we doing that? Because we want to get the value of N. We don't know what N is. Yeah, we only found M first. So this is what we want to get. So the rate of experiment 2. So if we come here, this is just going to be, let me try doing it here to avoid wasting time. So I'll just say experiment 2. So I'll do it from here. So now we're saying experiment 2 divided by experiment 3. So we have the rate. So let me just reduce this. The rate is simply 2.70 times 10 to the power negative 7 is equal to the K. The concentration is 0.1. N, this is 0.01. There's a 1 there. We don't care whether this is constant or not because we know it. The power there is N. It's M was 1. Then the second experiment, which is 3, the rate is 5.4. This is 40 times 10 to the power negative 7. Then this side we're having K, this is 0.01. N, then this is 0.01. This is 1 again. You notice that this part is going to cancel because they're the same, right? This part goes away. The K again goes away. So if we divide this, the rates, we are saying 2.7 times 10 to the power negative 7 divided by 5.4. This is giving me a 0.5 again. Then this side I'm dividing 0.1. I'm dividing the 0.1 divided by 0.01 because they are raised to the same power. it's giving me, so this side is supposed to give me, oh, this is 0.2. Yeah, so this was 0.2. This is supposed to be 0.2 here. Sorry, this is 0.2. When we divide, this is giving me 0.5 to the power n. So here the bases are the same, so it happens that n is also equal to 1. So now that we know, so we can come back here, we know the rate law. So the rate law is simply equal to the rate constant. We put the ammonia here, plus there's a 1 there, and the nitrogen dioxide. So when they say, given the data table below, find the rate law, this is the rate law there. Then the order of each reactant, the order of ammonia is 1, the order of the nitrogen dioxide is 1. So the total order of the overall order of the reaction is what? Is 2. So this is a second order reaction. It means it depends on 2 things for the products to be formed. That's what it means. And we can now get the rate constant. So I should have added how we get the rate constant. I should have posed it as one of the questions. To get the rate constant, which is K, that's the only time we get to use the units. So to get the rate constant, you pick any trial from the trials that are given. So I'll choose experiment 1. You put the rate, which is 1.37 times 10 to the power negative 7. This is molarity. Concentration per second is equal to, we are looking for K when you have the concentration of ammonia 0.1 molarity to the power 1, and you have the concentration of the nitrogen dioxide ion to the power 1 as well. We're looking for K. So according to what we have here, your K is simply going to be, so if we solve this now, so your K will just be, your K is equal to the 1.37 times 10 to the power negative 7 molarity per second. Here you had, I've just divided together by this. I've divided both sides by this, so I'm having 0.1 molarity and 0.005 molarity. So if we divide 1.37 times 10 to the power negative 7, so according to my calculation, if I divide this by 0.1 times 0.005, my answer is giving me, so my K, I'm getting a 2.74 times 10 to the power negative 4. This was molarity per second divided by molarity squared, because this is m times m, right? So when you cancel this, this is just going to give you, this is a 4 here, by the way, sorry, this is a 4. When you do your dimension analysis, the units of the rate constant are simply going to be per molarity per second. It's just going to be, because here it's going to be m over s times 1 over m squared. 1m and 1m go, so it's just 1 over ms. This is the same as per molarity per second. So these will be the units of the rate constant. So this is simply the rate constant connecting the rate of the reaction and the concentrations of the reactants. So this is a typical illustration of how a question involving the rate law can be posed. So just to make things interesting, let me give you another example. So another example is here. They are saying the reaction of nitric oxide with hydrogen is given at this temperature. This is what you're having. This is what you have. So according to this, you know what you anticipate. The rate is equal to, you put your K, just put the reactants. This is what you have. Put your N there. Then put your hydrogen. Then put your what? Put your M there. That's what you have. So they have told us, they're saying, from the following data collected at this temperature, determine the rate law, the rate constant, and the rate of the reaction when. This is what you are given. So this is the table that you have here. So look at the table that we have. They've given us the concentrations of the nitrogen monoxide and the hydrogen and the rates this side. So I want you to pause the video to see if you're able to get the N and the M before you continue, before you play it. Okay, so if we were to continue with this, I hope you've attempted it. We are going to choose 2 experiments where one concentration is kept constant and one is changing. That's what we said. So we're going to pick experiment 1 and 2 because the concentration of hydrogen is kept constant, right? So we're going to divide experiment 1 and 2. So we're just saying rate 2. Then they decided to use a rate 2 divided by rate 1. So this is what they did, and it gave them the power of the order of nitrogen monoxide. They used the letter X, so to them they got their X to be 2. That's what is there. And they do the same. They pick 2 trials. So you already chose experiment 1 and 2. It helped you to get the order of what? The order of nitrogen monoxide, because it's the one that's changing. Then once you do that, we're now going to choose 2 experiments where the nitrogen monoxide is constant, which is experiment 2 and 3, while this other guy is what? Is changing, so that we get the power of hydrogen as well. So according to their working, the overall reaction is simply the order of nitrogen monoxide is 1, the N is 1, so N is 1, and the M they got, the N is 2, the M they got is the one that's 1. So the overall order is that this is the third order reaction. So this is the third order, meaning it depends on 3 things. Is it true? If you go back, you find that it's true, because look at what you are having. So if we were to neutralize this, what I mean by 3 things is that this depends on nitrogen, oxygen, and hydrogen to produce these the products that we have. So it entirely depends on 3 things. No wonder the order of the reaction is 3, because there were 3 atoms initially. Yeah, so this is basically what we do to get the rate law. Now, this is always the case whenever you are given an experimental data table. So here they even went further to get the rate constant. So the rate constant was gotten to be this with the units indicated. So this is what they got. So for more examples, you can check your Zoomda. There are examples that are done at the end of the topic, or the PDF, the chem key point that I once shared in the group. It has very nice examples that you can use. Sometimes they can give you 3 reactants. So if there are 3 reactants, it simply means that you're going to choose 2 experiments where the concentrations of 2 reactants are kept constant. Only one is changing, because we need these 2 guys to cancel so that we find the order of. So it will be the rate is K. You put the N there. You put your B. You put your M if you want. You put your C. You put your P there, right? So we need to find each letter so that we get the overall order of the chemical reaction. There's a very nice suitable example in Zoomda. Yeah, so somewhere here, this guy here, the reaction is here. This is experiment number, if you go in Zoomda, it's example number 12.1. That's chapter 12, example 1, and it's on page 562. So this is a very nice illustrative example. We're trying to get the values of of N, M, and P. So they gave you this table, so you have to use this table. So the first time you choose experiment number 1 and 2, because this is kept constant and this is constant, while this is changing, so that these will cancel. Then you get the value of your N. Again, you're going to choose experiment number 2 and 3. So 2 and 3, let me use blue. So again, you're going to use experiment 2 and 3, because these are constant, while this is changing. So meaning you found the value of N. M. This is giving you M. Then this is N. The power of this guy is N. The power of this is M. We're looking for P. So to get the P, you're now going to use experiment number. Let me use a green one. You use experiment number 1 and 4, because these are kept constant, and this is constant, but this guy is changing. So this is basically how you play around with this. This is what you have. This is whenever you are given the rate law. Now, the same way that you have in mathematics, you have so many functions, right? But there's only a limit. There's only a certain scope. There's only so much to look at, so that we don't waste time to try to study everything. No, we just generalize it, right? So this is just a general form of how you can get the rate law of an expression, provided you have the experimental data. Now, there are those functions in mathematics. There are those functions that you need to know stuff about, like, let's say, quadratic functions, polynomials. But there's so much to know when it comes to functions. There are even functions with x to the power 10, x to the power 14 or 20. Yeah. So for you guys in first year, the coverage is limited when you are studying your functions, right? Same applies here in chemistry. We're just saying, in as much as we can get the rate law and get the orders, the order can be alternating. We are just from finding a third order reaction. So there these type of reactions that we need to know information about, so order of reactions, the ones that we know stuff about, right? These ones we even know how to sketch them on the what? On the graphs. So the first type of reaction, the first type of order is called the zero order. So the zero order is very interesting because it's only reaction where the rate constant is equal to, because the zero order means that the reactant is raised to the power 0, right? Because we say the rate entirely depends on the reactants alone. That's what we said. So if you have a zero order, it simply means that the rate of the reaction is independent of the changes you make on the concentration or with the concentration. In short, we're just saying it's the only reaction where the rate is equal to the rate constant as well. So the rate of the reaction is going to be constant throughout the whole experiment. There's nothing that you can do to the chemical reaction to change the speed. You cannot slow it down, you cannot increase it. Any changes you make with regards to the concentration of the reactant will not affect the chemical reaction. It will always be the same. That's basically what we are saying. So this expression that I give you here is called the differential rate law. It just tells us what the zero order is all about. Now, if you want to, this is the differential rate law. So this is with regards to concentration. Now there's what you call the integrated rate law. So we can relate this with time. We're saying the integrated rate law of a zero order reaction is, if you're looking for the final concentration after a certain period of time, you need to multiply it by the rate constant times that time plus the initial concentration that you had. This is what we call the integrated rate law of a zero order reaction. So it's like that equation you have in mathematics is the same as this, guys, just that here there's a negative, so goal. It's like this. You notice that the k is simply the gradient and it's negative. This even explains the following diagram I'm going to sketch. For every zero order reaction, when you plot the concentration of a reactant against time, you notice that the slope is just going to be going down like this. This is a zero order reaction. It has a negative what? A negative slope. That's how you know to say I'm dealing with a zero order reaction, because the concentration will be decreasing at a constant pace. This is what we have in terms of a zero order. And the other last thing we have to talk about is the half-life. So according to your biology or your grade 12 physics, half-life is what? The time it takes for something to be half of what it was. If I give you 100 kwacha, how many hours is it going to take for you to remain with a 50 kwacha? Half of 100, right? That's simply the half of life of that 100 kwacha. So it's simply the same analogy that we use when it comes to concentration. How much time is taken for us to have half of whatever that we started with? That's what we mean by half-life. And for a zero order reaction, the half-life can be gotten by simply using the initial concentration, whatsoever you had, divided by 2 times the rate constant. That's how you get the half-life of a zero order reaction. On the graph I showed you here, the one that I'm from sketching, we're just saying we're plotting. Whenever you plot concentration against time in a zero order reaction, it's always going to look like this. This is what you have. If it looks something else, meaning it's not a zero order reaction. What I mean is that you'll see when the tutorial sheet is out, they'll give you, let's say, time. Right? They'll give you 0, let's say 2, 3, 4, 5. These are time intervals. Then they'll give you the concentration of something like A. They give you my concentrations there. That is decreasing. Then they'll ask you to say, determine the order of this experiment. So when you plot the concentration and against time, plotting a cheaper graph, when you plot them, if it's not coming out as a straight line like this, meaning it's not a zero order reaction. When you plot, your concentration should be on the y-axis, your time should be on the x-axis. It should come out like this if it's if it's a zero order reaction. So don't force it. If it doesn't come out like this, let's say it comes out differently. Let's say it comes out like this, meaning it's not a zero order reaction. Something is wrong, so we don't have to force it. We check for something else again. Yeah, so in short, I'm just saying the same way that you have a lot of functions even as we have this general thing that we are from doing of finding the rate law, the N and the M, the table, and you're given experimental data. But the same way again, when you talked about, you went further to just talk about rational functions, quadratic functions, radical functions, modulus functions. So it's the same thing even here. We're just saying, let's limit the scope of the orders that we should be focused on. So the first one we're discussing here is a zero order reaction. A zero order reaction is a reaction where the rate of the reaction is equal to the rate constant, simply meaning that the rate at which the reaction is happening is independent of the changes we make to the concentration. We have two equations. This equation is just for formality, for us to explain what a zero order means. When there's a zero there, it means any changes you make here will affect the rate by a zero factor. Then the formula that we'll be needing for our calculations is this guy that I've written here, the integrated rate law, which is the rate law that shows the relation of concentration with respect to time, and it also explains why a zero order has a negative slope if we plot the concentration against time. And the half-life of a zero order reaction is simply the initial concentration divided by 2 times what? The rate constant. So this is the information you need to know about a zero order reaction. Then the next thing that I'll talk about is number 2, the first order reaction. So just from the name means there's a 1. So the differential rate law of a first order reaction is that there is A there, there's like a 1 there. The integrated rate law is ln of the final concentration to be equal to negative KT. Then we have plus ln the initial concentration. So the ln where I'm talking about here is on your calculator. If you look at the first on the right where there's an on button, if you're using a scientific calculator or a cash or something, there is a part where there's E, the natural log, the inverse of the natural log. So ln is a function. You have to punch it. So I hope you are seeing the number. If you are seeing it, try to verify that you're able to get ln 2 is the same as 0.693. So just try to check this. If you can't get this, please try to contact me so that I guide you on what the ln function means. Yeah, so that I just share more or shed more light here. But it's just a function. You click it, it's there on the calculator. So if you click ln 2, it's going to give you 0.69. It's a big number, but I'm just rounding it off to this. So I hope you've seen it. So we're saying for a first order reaction, any changes you make with regards to the concentration, it will affect the rate of the reaction by a factor of 1. That's what we mean. And the graph of a first order of reaction, the graph is simply when you plot ln of the concentration against time, the graph is always going to be facing down as if it's a zero order. Hope you are seeing the difference here. Here we're not plotting concentration against time. We're plotting ln of every concentration value against time. So like I was saying previously, to say if you find that you're trying to plot concentration and time and it's failing to look like it's a zero order reaction, you don't even stress. You make another column and start punching ln of every concentration. So you punch ln of this, you put your number there. Ln of that, you put your number there. Ln of that, you put your number there. Then plot these ln values and the time to see if it's going to come out as a first, as like this, meaning it's a first order reaction. So it's a trial and error process. And the half-life for a first order reaction is simply given as ln 2 over k. No wonder I gave you ln 2 previously because I need you to be familiar with that. So ln 2 over k. This is just the formula. It's the only half-life which is independent of concentration. It doesn't depend on concentration. So ln 2, some books they will give it the same as 0.693 divided by the rate constant. Because when you punch ln 2, you need to get this according to your calculator, right? So we are saying we have the zero order reaction, then we have the first order reaction. This is what we have. And these are the equations that we need whenever we're going to be dealing with questions. Yeah, so in this video, I'm just trying to explain the whole topic, all the concepts you need. Then there will be a separate video, which is going to be available for those that have registered, that will just talk about questions, just practical questions on how we can apply these formulas. Most likely, I'll use the tutorial sheet for last year, for 2024. So this is what you have in terms of the half-life for a first order reaction. Then the last one, last but not the least, we have a second order reaction. So we have so many orders of reaction. Like the other example we're saying, we got the third order reaction when you solve it using the data table. But here we're just saying the ones that we know so much about, that we can even plot. So this is a second order reaction. So second order reaction can either be having the following type of differential rate law. You can either have this, or we can depend on one thing twice, or you can depend on two things separately. Depend on A like this, then depend on B like this. This is basically what you're having. So this is still a second order reaction because 1 plus 1 is still 2. And if you're looking forward to get the integrated rate law of a second order reaction, this is what you're going to get. If you're looking to get the final concentration, when you know that the rate constant and the time and the initial, you can use this equation to find out how much remains after a certain period of time. And if you're also interested to get the half-life of a second order reaction is also the same as, so this is the same as 1. So this is the same as 1 over k. Then you have the initial. This is the equation for the half-life of a what? Of a second order reaction. This is the equation that we have there. This is what we're having. So these are fixed equations that you have to master by heart. You have to know this because in Chem, for those that are doing this at Wunza, they'll not give you the formulas, just the question. Then the data will help you to extract what you need. But those from Unilabs, you guys are given formulas, so this is still okay. You just look at your formulas, then you can just try to figure out how to apply it. And the graph for a second order, so the graph for a second order is the only graph which has a positive slope. A slope, the gradient is positive because it's the only one that goes up. We plot time against 1 over the concentration. So this is what we do. So like I was explaining, if you are trying to prove, they just give you data, like they give you concentration of A. Let's say Iyakanga, it's not coming out as a what? As a 0 order. And also ln of A, this is not coming out as a first order. You proceed, you start getting 1 over every concentration, 1 over every concentration value that you have. So 1 divided by this, you put your answer there. 1 divided by this, you get your answer there. 1 divided by that, you put your answer. Then try to plot this against this. One of them should work out. That's how you get to determine the order of the reaction if you are given the data in terms of the time and the concentration of a species or a certain reactant. So now we are saying, aside from these 3 orders, it's not all the time that the reaction is happening at standard conditions, because remember, we talked about factors that can influence the speed of a chemical reaction. But throughout these calculations, you notice there's no pressure, there's no temperature. We're not even considering them. Why? Because we are taking the best case scenario where those factors are kept constant. Now, what if those guys here are going to affect the whole reaction? What if they come into play? What if we consider them? Yeah, so let me just say, just use this, the Arrhenius equation. Yeah, so there is an equation that can help us to understand this. Before I give you the equation, I would like to explain what we mean by the collision theory. So I'll remind you of what activation energy means. So activation energy is simply the energy, the minimum amount of energy you need to kickstart a chemical reaction, right? So look at temperature 1 and look at temperature 2. So below temperature 1, let me paint this in white. Below this area here, you are seeing the number of molecules that are colliding, right? They are few as compared to the ones that are colliding in under or below T2. We're just saying if a reaction is endothermic, that's the case we are taking, and the temperature is increased, there's going to be more particles colliding and more products will be formed. Yeah, so the collision theory just states that the more the temperature, the more faster the collisions are going to happen, and hence we're going to have more products at the end at a higher temperature. So provided T2 is greater than T1, meaning the reaction is faster at T2 as compared to T1, and the Arrhenius equation suggests that we can actually get the activation energy if we know the 2 temperatures and the rate constant at each particular temperature that you are given. So the equation just states that ln, So this just states that ln K2 over K1 is equal to the activation energy over the universal gas constant is equal to 1 over T1 minus 1 over T2. The temperatures have to be in Kelvin. The activation energy will be gotten in joules per mole because the universal gas constant that we use here is 8.3145, which is joules per mole of every Kelvin, because there's no pressure that was mentioned when we're using this universal gas constant. So I'll just, because of my laptop trying to be it's running low, so I'm going to just showcase you an example that was solved using this particular equation here in Zoomda. So this is sample exercise 12.8. It can be found on page 557 in Zoomda, the 8th edition. So this example here, they are saying at 550 degrees Celsius, the rate constant of this reaction is 1.1 liters per mole. So we're just saying the temperature 1 is simply 550 degrees Celsius. You can convert it to Kelvin. This is what they were doing. The 550 becomes 823. Then the 625, the rate constant is 6.4. So T1 gives you K1. T2 gives you K2, because the rate of the reaction will differ depending on the temperature that you're dealing with. So this is on the collision theory here. So T2 has K2 and T1 produces K1, and you notice that K2 is always going to be bigger than K1. So this is basically what we are having here. Yeah, so once you do the replacements, when you are doing the replacements here, the K2, the K1, when we are solving for the activation energy, you punch it nicely. So you're going to say ln, open brackets, 6.4 divided by 1.1. You put your answer there, which is going to give me something like 6.4 divided by 1.1. Then ln our answer. That's giving me 1.76. So here I'm getting 1.76. Then there's a 0.98. Everything else is equal to activation energy over the universal gas constant. Now people have a challenge when it comes to punching the inside part, and I'm trying to do this for us here. So you just punch it the way it is. It's 1 over 823, then minus 1 over 898. So you get your answer to be a 75, everything over a 73. This is 9054. Then from here you can cross multiply. The bottom part is 8.3145, and the bottom part here So when it comes to this equation, we're just saying, sorry, the thing had muted. So this is what we are having here. I'm just trying to show you how we solve for this expression. This is what we have. We are replacing, I just divided 6.4 divided by 1.1. Then ln the answer you get 1.76 is equal to this part here. Subtract the inside part. It will give you 75 over 73, 9054. Then here you just cross multiply the top part times the bottom part here, these two, this times that times that. This is what you're having there. 75 times EA, that's 75 EA. Then we divided both sides by 75. So EA is going to be 1.4, now 10 to the power 5. This is joules per watt per mole. This is what you'd get. So this is the whole topic. These are the only things that you need to know on what? On chemical kinetics, and maybe to just cement your understanding, I would really insist that you show me what you get in terms of the calculation of the rate law when you are given a table. That's the backbone of chemical kinetics. Yeah, the rest of this is just for your own information, but you have to master the three orders we're from discussing, and also the Arrhenius equation, which is used whenever you have two rate constants and two temperatures. But the common question you ever find are these type of questions here. So just maybe to spice things up, I would like you to just if you're feeling as if you understand what we are doing, So this is going to give you the rate law to be K. Then we have what? Iodine I, N, and you have S2OH2 negative. This is M. So use this information here to get the value of N and M. Then feel free to inbox me for more questions to practice so that we see if you understand what you are doing. So this is my WhatsApp line. Thank you so much for watching.